for the organization of the symposium and also for the opportunity to give the talk. I'll be talking about dynamic fracture model and quasi-static fracture evolution. We talk a little bit about the main goal of the talk. So we are interested in studying the relations between a dynamic model and a quasi-static model. So basically, a fracture model started with Griffith's work in 1920s. And after that, I think the engineering community has been doing some works. But the mathematics community really started to look at this problem after a work from Francfort and Marigot. This was back in 1998, and they worked on quasi-static evolution. So they assumed that you have elastic equilibrium all over the time. Okay. Dynamic models have been mostly not considered, except by a model that was developed by, well, not considered by the mathematics community, right? So Chris, with Bourdin and Richardson, they proposed a model for dynamics fracture propagation. And this was back in 2011. And as far as I know, this is the first model where there is a mathematical theory for it. So mathematical theory, I mean existence of solution for the problem. And basically here, we somehow, the main question behind this is to try to validate the dynamic model, okay? So the question is, if you do a slow motion in your dynamic solutions, does this converge to quasi-static evolution? So this is the main question. So this was Griffith's criterion, okay? So his theory is the following. He states that when the crack grows, you increase the surface of the material, right? So there is an increase in surface energy. And this increase in surface energy has to be balanced by a decrease in elastic energy. So this is his criteria. And he assumed that the surface energy is proportional to the surface area of the crack. An important thing to note is that, well, he considered, let's say you have a material here, and then you have a fracture that's already there, and then he considered a path here, right? So the only way the fracture could grow was along this path. So this was his assumptions. So Francfort and Marigot in 1998 proposed the model for fracture evolution based on Griffith's criteria. Okay? This model was further developed by Dalmasso and Toder. This was 2002. And, well, they considered the problem in 2 dimensions. And the existence of, and they had some more technical assumptions about the crack itself. And this model that I'm presenting here, I think it was, the existence of solution for this model was proved by Francfort and Chris. So basically, that's the point, right? You have a sample of material is represented by a domain omega, which is contained in Rn. The boundary is Lipschitz. A function u in SBV represents the dislocation of the material in the n+1 direction. So this is the anti-planar case, right? And the fracture evolution is represented by the jump set of u plus the union of the points where U is not equal to G. So G is the boundary condition of the dislocation. So this corresponds to a fracture in the boundary. Okay? So the evolution is quasi-statics, kinetic effects are negligible, and the material is assumed to be in equilibrium at all times. So the evolution satisfies the irreversibility condition. So once the crack grows, it cannot close and disappears. It can only keep growing. Then you have this minimality condition here. And you also have an energy conservation. Okay? And as I said before, this model here in Rn, the existence of solution for this was proved by Frankfurt and Larsen. Well, it happens that this model involving the SBV functions is not really suitable for numerical approximations. Okay? And then back Bourdin, Francfort, and Marigot, in 2000, they proposed the numerical approximation for this problem. And the numerical approximation for it was based on the Ambrosio-Tortorelli approximation. The idea was to get rid of the SBV functions and start with a variation, have a problem where you have variational formulation that you can use like finite elements method to solve the problem, right? So the Ambrosio, so the idea is we want to regularize, oops. You want to regularize this functional here, right? And
can we come back to the energy?
Yes.
Sorry. What is the difference? I don't understand the energy. Sorry.
Well,
energy of
here is the energy.
And what on the previous row? It's the same thing.
On which one?
In the previous line. Sorry.
The previous.
No. Line. Same terms. Yeah, there are two lines, two energies.
First line, the first formula.
Yeah, two energies.
This and this. They're the same. Here you have an equality because this is the minimality condition, right? So this represents the fracture, and the fracture minimizes the energy with respect to all test function Z, right?
No boundary condition?
No the boundary conditions is somehow related, it's captured here. That's where the boundary condition is. Like the model allows the fracture to grow at the boundary.
Suppose there is no fracture on the boundary, then U is equal to G on the boundary.
U is equal to G on the boundary.
And the competitors, Z are also equals to G.
Is also equal to G in the boundary.
Yes, on the set is SBV omega. I don't know what they are on the boundary.
Really. Right. So basically, well, this part here regularizes the elastic energy, this one, and this part here, right? It's like the surface energy. So this approximates the Hausdorff measure. What is?
V. No.
Next one.
There is U. We have the U.
Okay, yes, I have the U and I have the V. Well, the V is a function that belongs to, it's bounded between 0 and 1, okay? So gamma here is a parameter of the Ambrosio-Tortorelli approximation, and gamma goes to 0. So when gamma goes to 0, the function V goes to 1 in L2, right? But the level sets, so this is the next transparency, the level sets the points x where V of gamma is equal 0, this approximates the jump set of Z or V or U, right? So the V function, you include a new function in the model, right? Before you had only U, and the V, the zero level set of V, captures the jump set of U. So that's the idea. So, so E gamma converts to E. So gamma converts to E, right? When gamma, little gamma goes to 0 with respect to convergence in measure. And so if U gamma and V gamma are minimizers of E gamma, and this guy here is bounded, then this function here converts to 1 in L2, and U gamma converts to U in measure, and U is also a minimizer of E. Okay, so that's, and this set here approximates the jump set of U, the S of U. That's the idea. So then we have the regularized quasi-static model. Okay, so basically here there's just, well, the first difference now is that the set gamma is captured by the function V. So the irreversibility condition now reads that the function V decreases with time. Okay? I have the minimality condition, which is pretty much the same with the functional E replaced by this regularized function. And I also have the energy conservation. Okay? So this is pretty much the same thing. Giacomini, back in 2005, proved that this Ambrosio-Tortorelli regularization of the quasi-static evolution does in fact converge to the quasi-static model, the SBV model. Okay, so he proved that the V times the V gamma times the gradient of U gamma strongly converges to U. This guy here converts to the energy, to the elastic energy. The surface term converts to the Hausdorff dimension of the fracture. And U, of course, is a quasi-static evolution. So it satisfies the Franco-Foer-Marigot model. So then there is a question that's, okay, a lot of attention to quasi-static models. And next, let's put more difficulty in the problem. So people started thinking on dynamic models. And, well, so they proposed the model. And the principle, the main idea was that the crack should obey a wave equation. And the principle for crack propagation should be the same as in quasi-static problems. Okay, so now we have a dynamic model for crack fracture propagation. So I have this, well, it's not actually a wave equation because I have this dissipation term here. Okay, this dissipation term is there to obtain some compactness and be able to prove that there exists a solution. So it's somehow artificial. The main goal would be to prove something when k is equal to 0, when kappa is equal to 0. Okay, so then the function U now satisfies a wave equation with dissipation, right? And G is the boundary condition. A of t is V squared plus eta of gamma. And this is the regularization parameter from the Ambrosio-Tortorelli term, right? Pardon me?
Can you give an idea why
Why to introduce? Well, because you want to do dynamics. So the easiest thing that's dynamic is the wave equation. It's the simplest, I think. But yeah, that's a good modeling question. Okay. Well, I think Chris is really interested in obtaining a model, a dynamic model involving the SBV problem, the SBV formulation. And this implies in taking gamma going to 0 in this model, and this is an open question, mostly because of the minimality condition. The minimality condition for the dynamic model, because the dynamic model we also have this minimality condition, it doesn't make sense if you take the limit gamma going to 0. Okay? So then there is also a conservation of energy for the dynamic problem. Okay? Our existence of solution for the dynamic model was proven by Larsen, Ortner, and Sully. This was in 2011. Okay? So now my talk starts. This is the problem that I'm going to present today. Right? So we consider a sequence of boundary conditions for the dynamic problem given by this function here, g epsilon, which is a function g scaled by epsilon. Okay? We set u epsilon and u sub epsilon and v sub epsilon. So these guys are defined in the time interval 0, 1 over epsilon, going to h1, h1, as the solution of the dynamic problem. Okay? And now we redefine this sequence of rescale solutions. Okay? So I have the US, the S belongs to the 0, 1 interval, and this US is u upper epsilon is equal to u sub epsilon S divided by epsilon. Right? So these functions u upper epsilon, they satisfy this condition here on the boundary. Okay? And the question we ask is that, does these functions here converge to a limit, and this limit satisfies quasi-static evolution? Okay, so that's the main question. And is there a condition to obtain that? Right. So the first thing is to obtain a priori estimates for u epsilon and v epsilon, and then define a limit through compactness. Right. So then we have this lemma here. Okay, and this lemma here is enough to give us the existence of u star and v star that are the weak limits of u epsilon and v epsilon in L2H1. So we also define the function a star s as v star s plus eta gamma. Right? So the question now is like, does these weak limits, these functions obtained through weak limits, do they satisfy the regularized quasi-static model? Right? So the main concern is this energy conservation. This is the step, like to obtain conditions that these functions here, the u star and v star satisfies this relation is the hardest part. So basically the condition is this. Well, there are versions of this condition. This one is like a more technical, let's say technical one, and then you have a more physical one. So we have this proposition, which says that if the function a epsilon is bounded in H1 L infinite by a constant c, and you have also strong convergence in L2 H1 of v epsilon to v star and u epsilon to u star, then this pair of functions here satisfy the quasi-static conservation of energy. Okay, so just give a brief idea of the proof, but is to these functions here, u sub epsilon and v sub epsilon, they are solution of the dynamic model. So they satisfy a conservation of energy, right? So I replace these functions in the conservation of energy for the dynamic problem, and I also obtain a similar relation for these two functions here, right? And then next, I show that if a epsilon converges to a star almost everywhere, then u epsilon, u star satisfies this equation. Okay, so Then I have this lemma here, which is like gives me some regularity. So the lemma assumes this condition holds. So, and if this condition holds and the function g is sufficiently regular, then u is also sufficiently regular, right? So this lemma here, and with this hypothesis, is playing the key role in the proof of this proposition, and the hypothesis, this hypothesis here, comes from this lemma, right? Well, the last lemma provides enough regularity to do this integration, to the kind of chain rule here, right? We proved the conservation of energy is equivalent to this relation, and finally we show that U epsilon and V epsilon satisfies this relation, and we take the strong limit we use the hypothesis of strong convergence to conclude that U star and V star satisfies these. Okay. So a key hypothesis in proposition 2 is this one, that the A epsilon remains bounded in H1 L infinite. Okay. So now we got stuck there for some time, and we were thinking, well, what can we do with that? And at some point, we realized that A dot is written this way, right? And well, here I have the upper epsilon and sub epsilon, right? But this guy here represents the speed of fracture propagation associated to the dynamic model, right? And then we can translate this condition here to a more physical condition. Is that we suppose there exists a function omega in H1, 0, 1, that the maximum speed of fracture propagation is bounded as follows. The maximum speed is bounded by the derivative of this function gamma, of this function omega. So the idea is that when you slow down the speed of the boundary displacements, the speed of fracture propagation also slows down. And if this is satisfied, then this assumption here holds. So this is the main proposition that guarantees that the functions U star and V star satisfy the quasi-static conservation of energy. So basically, I have to assume the strong convergence. In the beginning, I only had weak convergence. And I also have to assume that the maximum speed of boundary of fracture propagation is also slowed down when the boundary displacements slow down. Now I have to go back to minimality condition. Okay. The quasi-static problem, let me go back here. Satisfies this minimality condition. Well, this is the SBV version, and the regularized version satisfies this minimality condition. It happens that this minimality condition is a global minimality condition, right? And well, and assuming some convergence, this I already know that happens if this hypothesis to have conservation of energy hold, then I know that this condition here hold. Okay? I also assume the same strong convergence of U epsilon towards U star in L2 H1, but I have to assume an even stronger convergence to V epsilon toward V star, because it has to be in L2 H1, but also in L infinite. Okay? Then if these two functions here hold, I obtain a weaker minimality condition, because in this case here, U star is appearing both sides, and in this case here, I'm only varying the test function phi, right? So the minimality condition here is weaker. Because like the regularized quasi-static problem should satisfy this stronger minimality condition here. Right? So then we got to this question, right? Can we improve this and achieve global minimality? And this question has been asked before, because to treat the convergence analysis of the numerical scheme, you have to handle this question. So this question has been open for a little time, for more than 10 years now. Right? So we said, okay, what can we do? We don't think we can improve this result. But should this be an issue? And the question is, the physics of the problem says that this is not a big issue. Because, no, this might not be a big issue, right? Because the quasi-static model proposed by Francfort and Marigot is based in Griffith's theory, which is a local theory, right? So in some sense, you just need the points to be stationary points of the energy and not global minimizer, right? So Francfort and Marigot pointed out that the stationary property of Griffith's theory was replaced by global minimality due to the lack of mathematical framework. So they didn't have a framework that was able to treat the stationary property, and they decided, okay, let's put global minimality, right? People have already studied that, and Negri and Otne, they showed in 2008 that the solutions governed by minimality, by global minimality, might not agree with the ones provided by local minimality, right? So we claim the following. The weaker minimality condition could in fact be in accordance with Griffith's criteria and with the physics of the problem, with the real physics of the problem, under the following assumptions. Critical points of E gamma converge to critical points of the total energy functional E, right, from the Francfort and Marigot model. And also the mathematical challenge to relax the Francfort-Marigot model from global minimality to weak minimality can be overcome, right? Some partial answers to these questions are there. In 2009, Francfort, Lee, and Serfati, they proved that the first thing is true in one dimension, right? Also, people have been trying to develop framework with local minimizers for the Francfort and Marigot model, right? So Chris proposed something in 2010, and back in 2002, Dalmasio and Toder also created a model where they have a local minimality that's similar to what we have here, okay? So basically, we redefine a quasi-static, we redefine quasi-static evolution, which is the same as the regularized version of Francfort and Marigot model, but you have a weak minimality condition. So this condition here is the same that we obtained from our convergence from dynamics to quasi-static, right? The conservation of the energy is the same, and we have our main result. The main result basically states that if you assume that omega belongs to this thing, and the maximum speed of fracture propagation is bounded this way, also you have to assume the strong convergences, then the pair of solutions U star and V star is also a solution of this alternative regularized quasi-static model that we somehow proposed. And, well, I think this is all I have to say. I'll stop here.